Do you know this equation? This is the Henderson Hasselbalch equation, and it is heavily tested on the MCAT. This equation and the acid-base chemistry underlying it are really important for understanding how molecules behave in different pH conditions, whether or not they're protonated or deprotonated, and that can affect their function in our bodies. In this video, we're going to go through acid-base chemistry concepts related to the Henderson Hasselbalch equation and do a few MCAT-style questions to help you practice and get these points on test day. Let's start by breaking down the Henderson Hasselbalch equation and understanding the point of each variable. All right, let's work through this equation one variable at a time. See here on the left-hand side of the equation, we have the pH. This is the pH of the solution. All right, and often on MCAT-style questions, this will be physiological pH. Physiological pH is just a pH of 7.4 approximately. So if they say physiological pH, that's all they mean. So now we're saying that the pH is equal to the pKa, which is a measure of acidity of a functional group of interest. All right, so this is our measurement of acidity. Remember that the lower the pKa, the more acidic the molecule is, which means the more willing it is to donate a proton to the solution. The higher the pKa, the more basic the molecule will be, and that means it will be more willing to gain a proton from the solution. We're going to see how this plays out in action in just a moment. Our final piece of the Henderson-Hasselbalch equation is most of the time the reason why we use it. This is the relationship between the protonated and deprotonated states of a given functional group. So I don't love this notation. This is the one that you've probably seen in your book. You can see it's like A minus minus HA. What does that even mean? So I'm going to simplify this for you. The numerator here is just the deprotonated form. All right, so we're going to say deprotonated form of the functional group. Now that can be negatively charged or it can be neutral depending on the functional group we're looking at. So we have the deprotonated, or you could also call this the basic form. This is the form that is ready to accept a proton. On the denominator, we have our acid. All right, our acidic form that is willing to donate this proton, that's why it's got an H, and it's also the protonated form. So I personally, when I'm remembering my Henderson-Hasselbalch equation, I just think deprotonated over protonated. It's the easiest way for me to keep track of which one's on the numerator and which one's on the denominator. So acidic. So this variable basically takes the logarithm of the ratio between the deprotonated form of the functional group and the protonated form. Why do we care? Because whether or not a molecule or a functional group is protonated or deprotonated often defines its function, right? If it's charged versus neutral, that has a huge impact on how it's going to interact with enzymes, with other molecules, with some of our lab techniques like column chromatography. So all of this is relevant into how this molecule or functional group will behave in certain scenarios. So this equation, the Henderson-Hasselbalch, will say, hey, for a given pH and a given pKa of this molecule, will we have the deprotonated form or the protonated form of this molecule or functional group? Okay, so we have the basic definitions of each variable down, but it's easiest to understand the Henderson-Hasselbalch equation in action. So we're going to use a familiar molecule to help us understand the relationship between pKa and pH as it relates to protonation states of a given functional group. And that molecule that we're going to use is an amino acid. I just drew a generic amino acid here because we're going to focus on the carboxylic acid and amino groups for every amino acid to show why it has certain protonation states in a given pH. So I've gone ahead and drawn our carboxylic acid in its protonated or acidic state because it has its proton that it's willing to donate, and its basic state would be COO minus, right? That's going to be our basic or our deprotonated form of our carboxylic acid. Now, it's important to note that when we're working with the Henderson-Hasselbalch equation, if we're using pKas, we have to go one functional group at a time. If we wanted to look at the molecule as a whole, we would use the pi, which is the average of the two closest pKas in the molecule. But right now, we're going to focus on pKa. So I'm going to tell you that the pKa of the carboxylic acid is about 3. All right, and we're going to place this in a pH solution of 7. It's going to be roughly neutral or roughly physiological. And now I'm going to ask you, if we have a pK of 3 at a pH of 7, are we more likely to have the basic form of the carboxylic acid or the acidic form? You may know this content already, but let's go ahead and prove it with a Henderson Hasselbalch equation. We're going to do that up here. So again, our Henderson Hasselbalch is pH equals pKa plus the log of the, again, I'm just going to write base over acid, right? Because that's easier for me to use and remember. It's the concentration of base or the concentration of acid. So we have two of the three variables. We're good to go. So our pH is 7, our pKa is 3, and then our log, again, of base over acid. So go ahead, take a second, do that math, and see if you can tell what is our ratio between base and acid. Okay, let's do it together. 7 minus 3 is 4. So we have 4 equals the log of base over acid. Writing a little small here so we have room. Now remember, for logarithms, we can do a logarithm trick for log base 10, where anything in the parentheses, what we're going to do is we're just going to take that 10 and we're going to take the 4 on the opposite side of the equation, and anything in the parentheses is going to equal 10 to the 4. 10, and then we bring the number on the opposite side of the equation up on top of the exponent. So we can say, all right, the log of base 10, base over acid, equal to 4. That means that whatever's in the parentheses, so base over acid, is equal to 10 to the 4. Cool? So that means if we're creating a ratio 10 to the 4 over 1, that means that we are going to predominantly have the base form 10,000 times to 1. It's more likely that we're going to get the base form over the acid form when our pH is 7 for our carboxylic acid. Pretty cool, right? Let's go ahead and try that now with the amino group. All right, so the amino group on the other side, I'm going to tell you this amino group is more basic, right? Our acidic carboxylic acid has a low pKa because it's more acidic. Our amino group tends to be more basic. I'm going to go ahead and tell you it's got a pKa of about 11. Now, of course, to be more accurate as a base, we would write pKb for the basic reaction, but typically in science, especially in acid-base chemistry as it relates to organic molecules, we'll tend to use everything in pKa, and then just the numbers bigger than 7 are the ones that act as bases. All right, so we're going to use the Henderson Hasselbalch equation to determine, are we going to be in our basic state, right, our H2N, which is our deprotonated state, or our H3N+, which is our acidic state. Because again, this is a different functional group, so the acidic state for the carboxylic acid is neutral, the acidic state for the amino group is positive. That's why it's easier to think about it as protonated and deprotonated, because the charge actually depends on the functional group. So go ahead, try this on your own using the Henderson Hasselbalch to determine if we have the acidic or the basic form of the amino group. All right, so I'm going to draw this up here. Our pH again is 7. And we now have a pKa of 11 plus the log of base over acid. 7 minus 11 is -4 equals our log base 10 of base over acid. Again, what we're going to do is we're just going to take the exponent and the number here, pop it on top of the exponent to equal what's inside the parentheses. That's how we cancel out the log. So 10 to the -4 equals base over acid. 10 to the -4, we can rewrite as a fraction as 1 over 10 to the 4. That's taking the reciprocal. So we can see here that we have 10,000 times more acid form than base form for the amino group. So the acid form is preferred when the pH is 7 for the amino group because our pKa is 11. Now, this is a lot of math, and you're like, oh no, this will suck if I have to do this on test day. We can now simplify all this math down to a few key rules, because this will always be true. If, this is now our key rules, I'm going to go ahead and scroll a little bit so we have some fresh space. If our pKa is less than our pH, and I want you to think about the carboxylic acid, COOH, right, as our reference molecule, then we will be deprotonated. will be in our deprotonated form. If the pKa is greater than the pH, think amino group here, right? Amino, NH2, then we will be protonated. All right, and this will work for pI as well. All right, so if our pI is less than our pH, again, we'll be in our deprotonated form. If our pI is greater than our pH, we'll be in our protonated form. And of course, if our pKa is around equal to our pH, then we're going to be about 50%, 50-50 protonated and deprotonated. All right, so I'll go ahead and circle those here in our colors. So remember, base form will predominate if our pKa is less than our pH, and acid form will predominate if our pKa is greater than our pH. And now that you know this relationship, you won't really have to do the math. Remember that it is a logarithmic relationship, so a 10 to the 4 difference in base over acid content relates to a pKa pH difference of just 4, right? So the pKa and pH difference is a linear relationship, but it's actually representing a logarithmic scale difference between the values. All right, and we've just proved why amino acids are Zwitter ions at physiological pH. We've got a negative charge on our carboxylic acid and a positive charge on our amino group, making this overall molecule neutral unless it has a charged R group, right? So our acidic amino acids have carboxylic acid R groups, so they'll be negative, and our basic amino acids have amino-based R groups, so they'll be positive. I'm Amanda Brem, and I've been coaching students through their MCAT journey since 2019. Before we hit the Henderson Hasselbalch practice questions, please remember to subscribe to this channel for more videos on MCAT content, test-taking strategies, and mental fitness tips to help you perform your best on test day. And if you'd like more in-depth interactive lessons on topics like this one that also teach strategy, active practice, and preparing for test day, go ahead and click the link in the caption below, which will take you to register for my next available MCAT course. Okay, go ahead and pause this video, try this practice question on your own, and then we'll come back and do it together. All right, so this question says, the pKa of 2,4-dinitrophenol, shown below, this is the molecule, is approximately 4. So we have the pKa. At what pH, question mark, is dinitrophenol neutral and then negatively charged, respectively? So if we look at dinitrophenol, where it's going to deprotonate, where it's going to donate a proton is this hydroxy group, right? So that hydroxy group is going to become O-. So they're asking, when would we be neutral and when would we be deprotonated? So let's remember our rule. If pKa is less than pH, we're going to be deprotonated. In this case, that's going to be negatively charged. So we're looking for the pKa of 4 to be less than the pH, aka the pH needs to be greater than 4. So what we're looking for is for our pH to be greater than our pKa, which is 4, in order for us to be deprotonated for the second part of this question. So that means that our pH needs to be greater than 4. Let's look and see if we can find that answer. So both A and B show the pH being greater than 4 when we're deprotonated or negatively charged. So we can eliminate C and D right off the bat. Now we have to think about when it would be neutral. This is where our pKa being greater than our pH would result in it being protonated, right? Because protonated in this case is going to be neutral. So where are we showing that our pH is less than 4? A is the only answer that says the pH being less than 4 would be neutral and the pH being greater than 4 would be negatively charged. If our pH was equal to 4, we'd be 50-50, right? We'd be kind of in this equilibrium of protonated and deprotonated, so that's not going to be our answer. So another way we could have done this is by quickly eliminating B and D, because that is not going to be relevant to this particular question, and then going between C and A, which are saying opposite relationships. All right, if you have any questions on this practice problem, pop them in the comments below and we'll try out question number 2 next. All right, you know the drill. Go ahead, pause this video, try this question on your own first, and then we'll come back and do it together. Okay, so this question says that the pKa for the side chain of cysteine, which we know is SH, is 8.4. So we have our pKa equals 8.4. What is the ratio of protonated to deprotonated? Okay, so it's a little different than our setup for Henderson Hasselbalch. They're asking us for the protonated SH to deprotonated. I always like to draw the ratio exactly how I'm supposed to solve for it, so I don't accidentally put the wrong values in the wrong place. So the ratio of protonated to deprotonated, that means the protonated is going to be on the left side and the deprotonated is going to be on the right side. So I'm going to need to plug that in once I figure out the relationship. And they're asking, in a solution of cysteine at physiological pH. Well, we know physiological pH is 7.4. So we could do the Henderson Hasselbalch, we could figure this out, or we could think about this conceptually first. Let's try that. So if our pKa is greater than our pH, right? If our pKa is greater than our pH, what are we going to have? The protonated state, right? We know that from our rules. We're going to have the protonated state being preferred, right? So we know that we should have a bigger number for SH than we should for S minus, right? Because this is the protonated state. So right off the bat, we should be able to eliminate A and B, which says that we should have a more deprotonated, which is not true, right? So now we have to just choose between 10 and 1 and 101. Now we can do the math, and let's go ahead and do that, and then I'll show you a little shortcut. So we have 7.4 equals 8.4 plus the log of base over acid, right? We subtract it, we're going to have -1 equals the log of base over acid, which means that 10 to the -1 is going to be base over acid, or 1 over 10, right? 1 over 10 to the 1. So we're going to have 10 times more acid than base, which gives us C. However, remember how I told you that the pH-pKa scale was linear, but it represents a logarithmic scale? So the fact that we have a pKa and pH difference of 1 means that we could just take that difference and put it on the exponent. It's going to be a 10 to the 1 difference because in our pH scale, 1 point difference here equals 10 to the 1 in logarithms. So if the pKa had been 9.4, then our pH-pK difference would have been 2. We can put that on an exponent. It would have been a 10 to the 2 difference, and D would be correct. So you don't even need to do the Henderson Hasselbalch equation, even for questions that look like we need to, as long as you understand the relationship between the pKa-pH scale and our logarithmic ratio. If you have any questions on problem number 2, go ahead and put them in the comments, and we'll move on to our final MCAT style question. All right, you've got the routine down. Go ahead, pause this video, give this question a try first, and then we'll walk through it together. All right, this one's a little tricky, but we can do it. What is the pH? Now they're asking for pH of the buffer solution that is 2 molars in acetate ion and 0.2 molarity in acetic acid. So in this case, they're actually giving us the concentrations of the base form versus the acid form. They're giving us the pKa, and they're asking us for the pH. Right, so essentially, we've got, if we do our Henderson Hasselbalch equation here, log of base over acid, we have all of the variables here, and we're just solving for pH. So again, we're going to do this mathematically first, and then I'm going to show you some shortcuts. So first off, we need to know which is which in terms of the deprotonated versus the protonated form. So they're saying acetic acid and acetate ion. As a general rule, anytime they use the word acetic acid, that's in its acidic form, which is its protonated form. So this is acetate ion. I just put it here. It would probably not be given to you on test day, but the acetate ion, remember, it's just a 2-carbon carboxylic acid. This one is our deprotonated form, or our base form, and our protonated form is going to look like this. All right, and so this is going to be the acetate ion. Tate, ATE as our suffix, usually means deprotonated form of, right? So acetate ion is here, and this guy is going to be our acetic acid. Much like carboxylic acid is our protonated form, carboxylate ion, deprotonated form, just a terminology thing. So they told us we have 2 molar in acetate ion. That's going to be our base. All right, so we're going to plug that in. I'll plug that in down here. Right, so pH equals pKa of acetic acid is 4.76. 4.76. And then we've got plus the log of 2 molar, right? Because that's our base, it goes on top, over 0.2 molar, that's our acid, it goes on bottom. So now let's resolve the exponent here. 2 divided by 2 is just going to give us 1. Always with decimals, I like to convert it into scientific notation. So we have 2 times 10 to the 0 here over 2 times 10 to the negative 1. And 2 over 2 is just equal to 1, right? We'll say this is 1. And then we subtract when we divide exponents. So 0 minus minus 1 is 0 plus 1. So 1 times 10 to the 1, or 10. All right, so now we have a log base 10 of 10 to the 1. So we have a log base 10 of 10 to the 1. The 10s cancel when we do a logarithm. We just pull that 1 down. So we now have 4.76 plus 1 equals our pH. So that's going to give us a value of 5.76. So we can do the math, of course, but we can also still think conceptually. Remember, when pKa is greater than pH, we have the protonated form. But when we have a pKa of less than the pH, we have the deprotonated form. So we can see here that we have the deprotonated form more than 10 times more than we have the protonated form. So this rule is favored, right? Our pKa being less than our pH. That means that we can immediately eliminate A because we know our pKa is not going to be the same as the pH, right? Because we would have equal amounts. It would be like 2 molar and 2 molar if we had the same. So now we're looking at, okay, any of these would be fair options because any of these pHs would be greater than the pKa. But remember, it's only a power of 10 difference. 2 molar to 0.2 molar, that's only a 10 to the 1 difference, which means our pH difference to our pKa should be only 10 to the 1. So that's going to give us B. If this was 20 molar to 0.2 molar, then C would be our answer. 200 molar would be D. So again, we can do the math, of course. We can also think logically using our shortcut rule. All right, that was our last and most challenging MCAT style question on the Henderson Hasselbalch equation. Let me know how you did in the comments. And if you found this video helpful, please share this with your pre-med community. As we all know, studying for the MCAT can be hard and kind of lonely, and sometimes we all need a little help. Thanks so much, and happy studying.